Okay, so today we're going to talk about atomic spectroscopy, but we're going to apply it to stellar spectroscopy. So where do all of our atoms come from? They come from the fusion furnaces known as stars. So hydrogen is fused into helium, and helium is fused into heavier elements, and then those heavier elements collide with each other and fuse into even more heavy elements. And so we'll talk about this in the last section of the spring semester in thermodynamics when we get to nuclear chemistry. But essentially the most stable nucleus is iron. It's pretty flat there, so a lot of those elements around iron are very stable nuclei. So how do you get elements heavier than iron? We'll say like a barium and a krypton, which are lighter. Let's see, make sure I don't lie. Okay, so like a krypton's heavier than iron, so it's barium. Calcium. I know calcium has a pretty big cross section. So calcium can collide with other elements and make elements heavier than iron, and then other elements can collide with those and make even heavier elements. So I know that barium and krypton can collide and make uranium, because I know when you split uranium, you get barium and krypton. So you just look at the protons and add those up, and you can see what elements can collide to make other elements, and what elements, when they split, will produce lighter elements, and so on. So in those furnaces of the stars, the pressure is so high and the heat is so hot that Coulombic attraction and repulsion is not insignificant, but it can be overcome. So the repulsion of those nuclei can be overcome by the velocity of the nuclei, and they can hit and fuse. So that's where we get our elements. And so this is a solar and atmospheric spectrum. We can't really get a spectrum of the sun from Earth without also getting our atmosphere. But our atmosphere is transparent to visible light. And we see the general black body curve. So if we go back to look at the black body radiation curve from any hot object, we would have this typical shape where it would be low at long wavelengths and low at short wavelengths and big in the middle. And you could fit this to that Planck's curve, and you could figure out what the temperature of our sun was. So that's pretty neat. The sort of the black body temperature of a stellar object, you can fit to that black body curve, and you can get the temperature of that star. Then also, you notice that it's not smooth. There are some dips here. And I said this is the solar and atmospheric spectrum. The sun's coming through our atmosphere, and so if there are elements in our outer atmosphere, they're going to absorb light. So you see up here some of those lines are from oxygen, so O2, so A and B. So here's an O2 line. So that solar light's coming into our atmosphere and is being absorbed by oxygen here. And then B is also an oxygen line. And then hydrogen, well, we really don't have that much hydrogen in our atmosphere. But we look at this and we see sodium and iron. Now that's bizarre. We don't have a lot of sodium in our atmosphere. So what we're looking at here is the solar atmosphere. So I added this slide to the notes. So this isn't what you have, but I'll upload it later. So this is the sun, and being blasted out of the sun, are all these fusion explosions, right, are heavy elements, heavier than hydrogen, and hydrogen's being blasted out as well. And so we start to see this development of a cooler gas outside the solar flare area. And so this is where light's coming from the sun, and it hits some of those cooler atoms that have been spit out of the sun. So there's iron and sodium, and once they get away from the hot solar area, they capture electrons and they become neutral atoms. And so you've got sodium gas and iron gas around the sun. And so that light leaves the sun, hits that cooler gas, and some of that light disappears. So when it hits our eye, we're missing some of that light. And so we see a sodium dip, we see an iron dip. And so this is how we can tell the chemistry of our sun. We can also tell the age of that star because we can take ratios of the sodium to iron and other elements. And we can see how far along that sun is in generating heavy elements. I think it's pretty amazing that we can do atomic spectroscopy on an object that's so far away. This is 8 light minutes away. So it takes light 8 minutes to get from the sun to the Earth. Okay, so we're kind of looking into the past too. We see the chemical makeup of our sun 8 minutes ago. It doesn't change that fast, so it's pretty okay. So here's the spectral differences, looking at I forget which galaxy this is, but you can see with different satellites that we have looking at these stars, we see from the ultraviolet into the visible and into the infrared. We see sort of a composite picture here in the middle made up from data of all of these different spectral signatures that we have. So we can take a picture using different spectrometers of these different galaxies and see some of the characteristics of different elements in those galaxies and so on. And so let's talk a little bit more about cosmology. This is the standard cosmology right now. It's probably been one of the most tested physical theories in history. It's been for over 100 years. Physics has been throwing everything they have at this standard model. So at the beginning, you had this unknown physics of inflation. So the universe was essentially blown up like a balloon, and then it's been expanding ever since. But the expansion of the universe is different from the inflation of the universe. The inflation of the universe was faster than the speed of light. And we have no idea the physics that exists in that inflationary period. But once that's been blown up and inflated, then our current understanding of physics has seemed to have held through this whole time. Now, how can I say that our current understanding of physics has held for this whole time? Think back to those Fraunhofer lines. This is the position of the sodium dip, okay? And if we zoom in on that, we see a doublet. We see a sodium doublet. And we now know the term symbols for that sodium doublet. It's that doublet P 3/2 and that doublet P 1/2 line. Emission, okay? We see it in emission. We also see it in absorption. What does that spin-orbit splitting depend upon? You tell me. This is the discussion part of the day. So what does that splitting in sodium depend upon? All the physical constants that go into that splitting. What are some of the things we saw in our particle in a box energy equation? So what are some of the constants that go into that particle in a box energy equation? There's Planck's constant, right? The speed of light was not in that energy equation, but it was in the conversion of energy to wavelength and those kinds of things. So yeah, the speed of light. Mass of the electron, right? Do you think the mass of the electron is in the atomic orbitals energy equations as well? We saw that Hamiltonian. We developed those orbitals, and our theory is pretty good. We are able to determine those term symbols, those energy splittings, based upon things like the mass of the electron, things like speed of light, Planck's constant. What else? The spin of the electron. We didn't actually calculate that, but that has an actual value. That's a physical constant. And that spin-orbit coupling, the small magnetic moment for the electron and the magnetic effect of that orbital, those are all buried in there. Now, if our sun, the light we see from our sun, is 8 minutes away, we know that those physical constants that we measure in lab were the same 8 minutes ago. And we can look at stars in our own galaxy, which we can kind of measure their distances based upon parallax. So the Earth orbits the sun. We come over here on this side of the sun. We take a snapshot of the stars nearby. Okay, and then we go orbit to the other side of the sun. So we take a spring picture, then a fall picture, take another snapshot. And those stars nearby have changed their relative positions in these two snapshots. Essentially, we can get a 3D picture of the stars closest to us. But some of those are light years away, several light years away, thousands of light years away. And we see the same sodium dip, the same spin-orbit coupling. We see the same physical constants of mass of the electron. We see the same magnetic moments, spin-orbit coupling. We see the same physics. So we can know that our physics hasn't changed in the last several thousand years, and we can go back even further and see those galaxies that are, if we look also at this balance of distance and light, we can find stars similar to ours. And we can see that the brightness matches. So the farther away they are, the dimmer they are, as you might imagine. And we can calculate the dimness of those stars. Now, we don't want to pick stars that are different than our sun because we have a really good model for our sun. So we'll find stars like our sun, and we'll look at the brightness of those stars. And we can get a distance measurement with brightness for similar stars. And so then we can find stars that are even further out, have the same chemical makeup as our sun, and are very, very dim. And so that means they're even further away. And we see the sodium dip, and we see the same physics, the same spin-orbit coupling, the same ideas of Planck's constant. So we have this record of physics that goes back about 13.7 billion years of having the same constants, the same masses for electrons, the same spin-orbit coupling constants. And so we can say that physics, this standard model of physics, holds all the way back to this point. Then we have this deflationary period, which we're not sure about. And then they talk about quantum fluctuations, and I put question marks on that because that's a guess. Okay. So that's why I stamped that on there, because that has not been well established. So let's talk about this evidence for this expanding universe and how this works. So if we have our solar spectrum and we have this sodium line, we can look at the other stars that are far away, and we see the sodium line has shifted to the red. And so if we look at the spectrum of a sun similar to ours, we'll notice that these dark bands, which are called the Fraunhofer lines, this missing light, has the same pattern. You see there's a little doublet there, there's a really tight doublet there for sodium, which you can't resolve in this picture, and then this red line. And notice these have the same pattern, but they're red shifted. So when we talk about the red shifted light, evidence for expanding universe, this is what we're talking about. The atomic emission and absorption lines are what have been red shifted, okay, in that spectrum. Now this is something that you can get if that object's moving away from you. This is called the Doppler effect. Now it's the Doppler effect nearby, but here we're not actually looking at necessarily the Doppler effect, but more the expanding universe, just the change in spatial dimension. And so then we can look at this sodium line. So we zoom in on that, and we can see that the emitted line is 589 or 589.6 nanometers. We can look at the observed line. So this is from a distant star, and it's 591.8 and 592.4. So let's just pick a pair of these lines and calculate this Z value. This is the cosmic redshift. So for this particular star, we would calculate this difference in the emission and observed wavelength, divide by the emitted wavelength, and we get this 0.004749. So this is how we calculate the redshift of all of these different galaxies and stars by looking at these shifted atomic absorption lines. And now this is related to the velocity of the expansion. So if we multiply this redshift by the speed of light, we get the velocity. And then it's moving pretty fast. So we use kilometers per second. Think about that, kilometers per second. Run a 5K in 5 seconds. So here we have the speed of light. Since we got 4 significant figures, I went ahead and wrote it out to 4 significant figures. And it's times 10 to the 8 meters per second, but kilometer is 10 to the 3, so it's 10 to the 5 kilometers per second. That's how fast light is going. So that's pretty cool. 20,000 kilometers per second. And so we get this galaxy or this star is receding from us at 1,425 kilometers per second. So that would have caused this redshift. So that's the expansion. Now, Hubble, you've heard of the Hubble Space Telescope. Hubble's laws said that this expansion velocity should be linear with distance. And so the near distances, like I said, they match the orbital parallax. So as we go around the sun, we can take photos from either side and compare them. That's called parallax. And then also brightness versus distance gives us this scale here. So we can have the scale and distance. We can put those stars on the distance scale. We could do the redshift and we could get the velocity scale, and it falls somewhat on a straight line. And it's now distance is not just in meters. That would be ridiculous. This is parsecs, so that's a real thing. Okay, good old Star Wars. Okay, so one megaparsec. A parsec is 3.26 light years. I don't know why 3.26. I had to pull the thread on that. But a megaparsec is a million of those. So 3.26 times 10 to the 6 light years. Okay, so good job, Han Solo. So this ends up being the Hubble constant. If you find the slope here, it's 70.4 kilometers per second per megaparsec. And so if we take that, what we just had was that velocity that we just calculated and calculate the distance, we would get 20 megaparsecs for that star. So what would be the observed wavelength of the 589 line from a star 20 megaparsecs away? So this is how you would do this the other way. If you had a star and the brightness told you it was 20 megaparsecs, what would be the expected sodium line position? And so we do a little bit of algebra here. That's the distance, but we want to get this observed lambda here. So we're going to bring h to the other side, bring the speed of light into the denominator on the other side. We can rearrange this to where it's lambda 0 over lambda e minus 1. And so we'd bring that 1 on the other side and then multiply by lambda e. So that's the algebra to get to this point here. And so now we've solved for the observed wavelength. Putting all our numbers in, we'd get 592.4 nanometers. So that's how much that line would, that's where that sodium line would show up in a star that was 20 megaparsecs away, and it'd be receding at about 1,400 kilometers per second. Now, what's this little cluster here? This is pretty neat. Okay, this little cluster here shows a bunch of galaxies and stars that are either have too low a velocity or too high of a velocity. So what's going on when we see the redshift from those? They're all centered on a spot about 15 megaparsecs away. And this is a cluster of galaxies that is orbiting a supermassive black hole. And so they're moving around each other. So some on the bottom side are not just moving away because of the expansion of the universe, but they're moving away because they're spinning. And the ones on the other side of that black hole are coming at us. So they're expanding. They're redshifted from the expansion, but redshifted a little less because they're also coming at us. And so we see this cluster of galaxies right there in the middle that is orbiting this spot in space, which is pretty neat. And so you can put together a lot of interesting things about space by looking at Hubble's law and the redshifts of these galaxies. So that's how we're learning so much about objects that are so far away. And it requires chemistry because it's related to all of the atomic lines, like the magnesium line and the iron spectral lines and the sodium spectral lines. So we can learn so much about our universe if we understand atomic spectroscopy. So that's why I wanted to just give you this little bitty mini lecture on stellar spectroscopy, because it fits so nicely into atomic spectroscopy. You can do it the other way too. When did the emitted light leave that star from 20 megaparsecs away? Well, 20 megaparsecs is essentially light years. And so it was 65 million years ago. So it's 20 times 20 megaparsecs. So that's a long time. And how many meters was this? Well, that's a ridiculous amount of meters. So this is how many years? 65 million years. There's 365 days a year, 24 hours of the day, 3,600 seconds per hour, and then you have the speed of light in meters per second. And so then that gives you meters. So 6 times 10 to the 23rd meter. So it's a mole of meters. Which doesn't really count because meters aren't countable objects, but still. I thought that was a coincidence. I didn't make this happen. It just came out 6.1 times 10 to the 23rd meters, or 610,000 exameters. So even if we go up to the exa prefix that's 10 to the 18, it's still 610,000 of those. So that's pretty amazing. It's a long way away. So it took that light 65 million years to get here. It is crazy. And you think about that, it's like, how do we know that physics was the same 65 million years ago? We know because of the atomic spectral patterns. We see the same pattern for sodium, Same pattern for potassium, same pattern for iron, all of those things. So it's a beautiful thing. Now, there's more on this at this website, Physicist Michael. That's where I got some of this information. So you can go watch this YouTube video, and he'll rehash some of the stuff that I talked about. Let's do a little bit on the propagation of uncertainty.